everyone, thanks for joining in. I'm Sabine Storan from the University of Constance, and I will now present joint work with Mike Tim, also from the University of Constance, on the topic of the so-called multi-kind BahnCard problem. So BahnCard is a German railway pass offered by the Deutsche Bahn, which allows you, after purchasing it, to buy train tickets at a reduced price for a certain period of time. So mathematically speaking, a BahnCard is nothing else than a triple of these three values I just mentioned. So the purchase cost, the validity time period, and also this ticket price reduction factor beta, which multiplied with the original price then gives you the price you actually have to pay for your ticket. So of course it only makes sense to have beta between 0 and 1 excluded, because with a factor of 1 you would have no reduction at all. So for the free standard BahnCards, which are currently available in Germany, you would get the following values. So this is so-called BahnCard 25, which costs 62 euros, is valid for a whole year. And then if you have a valid BahnCard 25, you only have to pay 75% of the original ticket price. And there's also BahnCard 50, where you have a 50% price reduction. And there's also BahnCard 100, where you have to pay nothing at all anymore for any kind of train journeys which happen within the validity time period, but it's also pretty expensive. So a journey is nothing else in this context than just the date on which a journey happens and the respective ticket price. So we do not care for the destination, we do not care for the particular time, just on which dates train tickets will be purchased and at what cost. And of course, we will not consider only single journey in our problem, but a so-called journey stream, which is nothing else than a list of journeys sorted by their dates. And now we are ready to define the original BahnCard problem, introduced in 1998 by Rudolf Fleischer, and it asks on which dates should a BahnCard be purchased to minimize the overall cost for the journey stream. So of course these costs consist of the ticket prices, which may be reduced, and also the purchase cost of the BahnCard. So of course we could buy BahnCards like every year, maybe every 10th year, maybe you will buy one in March and then another one in next year at August, and so on and so on. So you have all these options available. So basically on each day you have to decide whether it will be worthwhile to purchase a BahnCard or not. And actually there are two variants of this problem, called the offline and the online version. So the offline version is God mode, where you know all of the train journeys ahead of you in your life until you die, so you can make fully informed decisions about what to do. And there's the more interesting and maybe more realistic online variant, where you don't know this journey stream sigma in advance, but at each particular date you only know what happened in the past, but you can't foresee the future. But there's one issue with the original BahnCard problem formulation, and that is that it only considers or allows one type of BahnCard. But as we just have seen here, there are actually multiple purchase options available, and also in related applications it's usually more complex than just to have this one option. And now the goal of this talk will be to introduce you to the multi-kind BahnCard problem and discuss some initial theoretical and practical results. So from now on we will consider k BahnCards instead of one, and each BahnCard has its own purchase cost and also its own price reduction factor. What we will assume for the ease of exposition though is that they all have the same validity time period t. So we see that this is in line with the example BahnCards from Germany I just showed you in the last slide. They are all valid for a full year, but I will come back to this issue towards the end of the talk. Alright, but if we now assume that this validity period is actually the same for all of the BahnCards, it also allows us to sort the BahnCards, and that is increasingly by price and decreasingly by price reduction factor at the same time. So this hopefully makes sense for you, that the BahnCard with the highest cost should also have the best price reduction factor, that is the smallest one, because if you would have a more expensive BahnCard which gives you less of a price reduction, you would never buy this one for sure. Alright, so we can now have an order on these BahnCards, and of course what is unaffected by these multiple purchase options is the journey stream. It just looks like it looked before, but now our question gets a bit more complicated. So we do not only ask on which dates should BahnCards be purchased, but also which BahnCards should be purchased on these dates. And this obviously makes our problem more complicated, as we now have more options to consider. But it also makes it more complicated for the following reason, which might be less obvious, and that is that it might be optimal to purchase a BahnCard while another BahnCard is still valid. For the one-kind BahnCard problem, this is never a necessary part of an optimal solution, because if you buy another BahnCard while the BahnCard of the same type is still valid, you just basically shorten the validity period of the BahnCard bought later. So it always would make sense to wait until the BahnCard which is currently valid expires and only then to buy a new BahnCard. But in a multi-kind version of the problem, this actually could happen, but it's really necessary to have several BahnCards being valid at the same time. And of course, price reduction factors do not stack in the scenario, otherwise you should always buy two BahnCard 50 instead of a BahnCard 100. But what happens, of course, is that your best BahnCard, so the one with the best price reduction factor, determines the price you have to pay. So now here's a small example which demonstrates that it really might be optimal, and in fact the only optimal solution, to have BahnCards with overlapping validity periods. And we have these two kinds of BahnCards here, basically a BahnCard 25 and a BahnCard 75. And we have these three journeys, and what you can see here is that the journey dates are spread out in a way that not a single BahnCard purchase can lead to a reduction for all three of them at once. So the optimal solution here indeed is to first buy a BahnCard of type 1 on the date of the first journey, and then on the date of the second journey already buy a BahnCard 2, although here this BahnCard 1 is still valid, but we see that the purchase cost and then the price reduction pays off for this journey here with the BahnCard of type 2, and then it also covers the last journey here, so we actually get a pretty huge reduction by buying this BahnCard 2 on this date, and this will give us an optimal solution cost of 655 euros. And actually it's really important to remember this observation here, and we will now discuss the offline variant of the problem. So remember that in the offline variant we know all of sigma in advance, so all of the future journeys with their respective dates and ticket prices, and so we can make fully informed decisions. So for the original BahnCard problem, considering a single BahnCard, Fleischer already proposed a very elegant graph-based solution here, and I will explain it to you on a small example. So we have one particular BahnCard and we have a journey stream here consisting of 6 journeys. And so the approach starts by creating a node for each journey plus one dummy node at the end. And now we connect these nodes by edges, which get costs which are equivalent to the cost of these journey prices. So to get from the first journey to the second journey, we pay 20 euros because this is the cost of the first journey, and so on and so on. And this also explains why we need this dummy node here at the end. So now if you just follow this path, this would just mean we never buy a BahnCard, we always pay the full price. So the summed costs along this path are just the summed costs of the original ticket prices. So now to model that we might also purchase BahnCards, we have to introduce additional edges, and we do it as follows. We consider each journey individually, and now we look at the journey date, and we ask ourselves, if we buy a BahnCard at this particular date, how many other journeys will it also help to be cheaper? So if you, for example, buy this kind of BahnCard, which is valid for 20 days on date 5, then it of course will also reduce the ticket price of the next journey here, because there's only a 5-day gap, but it will not reduce the ticket price of this journey here because the time gap here is too long. So now to model this in our graph, we introduce the edge actually from here to here, so spanning those two edges it actually makes cheaper. And of course the cost we assign here is the summed reduced ticket prices plus the purchase cost of the BahnCard. And now we go through all of these journeys and introduce all of these edges, which gives us the following graph here. And now to get the best solution, to compute the best possible decisions, we just have to compute the shortest path from this node to our dummy node at the end. And in this scenario it will look like this. So we would first purchase a BahnCard on the very first journey date here, and then we will purchase another BahnCard here, and then here for this last journey we would not have a valid BahnCard. And the size of the graph as well as the running time for this approach is simply linear in the number of journeys. So now what happens or what changes if we consider multiple BahnCards? Well, the first idea might be to just do the very same thing. So for each of the BahnCards, just introduce the respective edges we would also have introduced here. Now if you remember, so this is the example from the last slide, I told you that the optimal cost is 655 euros. And now if you look at the graph on the right, you will observe that it's not possible to get this kind of answer here. So actually the cheapest path here is 660 euro. And the reason for that is exactly our observation we made, namely that it might be optimal to actually buy a new BahnCard while an old one is still valid. And this kind of option is not encoded in this graph because, as you see here, if you buy a BahnCard of type 1 at this date, the first node at which you can purchase a new BahnCard is this node here. But actually, to make this work, we have to introduce edges not only to this latest point in time up to which the BahnCard is valid, but also to model this early expiration in some sense, these edges which are shorter. Okay, so not only for this last one, but also for all intermediate ones, we need these additional arcs to actually have all of our options encoded. And so we get a graph which looks like this. In the paper, we actually also introduce some pruning rules to make the graph even sparser, but the important message here is that we can now always compute the optimal offline solution within that graph, and running time increases a bit, of course, because we now have to consider these multiple options and also multiple endpoints of the edges, but it still allows for a very quick computation of this optimal solution, and this will then serve us as a very helpful tool in analyzing the quality of our online strategies. Speaking of which, we now come to the online strategies. So for the scenario where we do not know what journeys will happen in the future, but we nevertheless have to make decisions right now. So we of course hope that we are not much worse than in a scenario where we really know sigma in advance. And this is also our quality measure. So we compare the cost of our online strategy to the optimal offline solution. So in his paper on the one-kind BahnCard problem, Fleischer analyzes 3 online strategies called never, always, and some. And in the paper, we discuss generalizations to the multi-kind BahnCard scenario for all 3 of them, with the B-sum, so our generalization of the sum algorithm, being by far the best, so the one with the smallest competitiveness ratio. This is why I want to quickly discuss it here. So the B-sum algorithm says that we only buy BahnCard of type K, so the best BahnCard in terms of price reduction factor, and we do it whenever the sum ticket prices of our journeys exceed a certain threshold. So in the example here, if we have a BahnCard with cost 100 and a price reduction factor of 0.5, then we have a so-called critical value, which is 100 divided by 1 minus 0.5, so 200, which means we would sum up ticket prices until we exceed a value of 200, which would happen here at this point. And then we would have here our reduced ticket prices, and then we start over. So we start summing up here, 25 plus 120, and so on. And here is the next point where we exceed this critical value, so I would purchase another BahnCard. So for the one-kind BahnCard problem, this algorithm is 2 minus beta k competitive, so it's always bounded by 2, but can be better if this price reduction factor is rather large, so if the reduction is rather low. Here in our scenario, unfortunately, our competitiveness also depends on beta k minus 1. So I don't have time to explain this in detail here, but the idea is that the optimal solution could have a BahnCard of type K-1 or with an even lower index in a time period where our strategy does not have any available BahnCard at all. And actually then we can show that the competitiveness in that interval is bounded by 2 over beta K-1. And the good news is that, of course, if we follow our assumptions, beta K-1 cannot be 0, so this is bounded. Of course, if beta K-1 is really small, the bound is rather bad, but for our real-world example with the BahnCards in Germany, we actually observe that the second best BahnCard has a price reduction factor of 0.5, and so what we get here is a competitiveness ratio of 4, which is quite good. Furthermore, we propose a bunch of heuristic strategies. So here we cannot really prove a constant competitiveness factor, but we deem them to be useful in real-world scenarios. So I don't want to discuss them in detail, but maybe pay attention to the last one. So the idea here is very similar to the B-sum algorithm to always sum up ticket prices until a critical value is reached. But we consider all of the BahnCards here, not just the best one. And also we reset the sum, but we include also the reduced prices which happen within a validity period of a certain BahnCard. In our evaluation, we compare all of these strategies to the optimal offline solution in different scenarios. So we have the real BahnCards, but also artificial BahnCards, and our journey streams stem from different traveler profiles. And what we observe here, to summarize the results very quickly, is for the real BahnCards, where the red grid algorithm is the best algorithm overall, and the B-sum algorithm, although it has provable competitiveness, is sometimes even the worst strategy. Sometimes it's close to the performance of red grid, but red grid was still better on almost all instances. For the artificial BahnCard, so we got a more mixed picture and more diverse results, which you can find in the paper. So to summarize, what we've seen today is a graph-based optimal offline solution, as well as several online strategies for the multi-kind BahnCard problem. And of course, they could be improved in various ways. As I said, one important or interesting extension would be to consider different validity periods of BahnCards. The optimal offline solution actually works the same way, and also most of our heuristic strategies, but a B-sum strategy would need to be adapted. And also, there are interesting BahnCards in Germany which depend, for example, on the performance of our soccer team. So they do not only have different validity periods, but also flexible and unpredictable validity periods. So it would be interesting to incorporate that, and also to consider combinations of BahnCards and other price reduction offers, which of course would further complicate the problem, but would also make it more applicable to complex real-world scenarios. So with that, I want to thank you for your attention, and if you have any question, let me know.